We'll now be going over the answers to the identifying pedigrees practice. So here's a guide as to how to identify the pattern of inheritance for the different pedigrees. So the first pattern of inheritance for sex-linked recessive, the first thing is that there's usually more males than females, and that's because males only need to have one copy of the recessive allele in order to have the genetic condition. Because it's recessive, it typically skips generations, and when assigning genotypes, males are easier. And that's because a male, if it's sex-linked recessive, will either not have the condition or they will have the condition. But if it's a female, an empty circle could either be homozygous dominant or it could be a heterozygote, which would indicate that she's a carrier. If it's a shaded in circle, then that would be a female that has the traits. So if you determine that it is sex-linked recessive, the ones that are easier to assign genotypes to are the males. Now, we talked about how Duchenne muscular dystrophy, color blindness, and hemophilia are 3 different genetic disorders that follow the sex-linked recessive pattern of inheritance. So the next 2 are both autosomal. And in both of these cases, there's usually an equal number of males and females that are affected in the pedigree. The difference, however, is that in an autosomal dominant pedigree, anyone who has the condition usually also has a parent who has it. So, let me just draw a dividing line here. This situation would not be possible for an autosomal dominant condition. So if this was autosomal dominant, this person could be homozygous dominant or heterozygous. But in order for that person to have the condition, they would have to inherit this dominant allele from one of the parents, in which case that would mean one of the parents would have to have it. But that's not the case here. So again, any affected individual would have to have a parent who also has it. The genetic disorder that we discussed here was Huntington's. We didn't really get into any other autosomal dominant disorders. Autosomal recessive disorders, because the recessive allele can be hidden, those can skip generations. Now, I have a situation here where this is also not possible. The reason for that is because if these 2 people have the condition, then let's say these 2 people who have the condition are homozygous recessive. The only allele that they can pass on to their offspring, in this case the son, would be 2 recessive alleles. They don't have a dominant allele. But in this case, the person who's normal, the son who's normal, could either be homozygous dominant, capital R, or heterozygous. But that's impossible here. So 3 genetic disorders that we discuss with autosomal recessive include PKU, cystic fibrosis, and sickle cell anemia. So that's what we discussed with that. Now we can take these ideas and apply them here. So in an autosomal disorder, since it's not linked to sex, it's typical that it'll be equal amongst males and females. Sex-linked disorders will be more often in males. And anyone with a dominant disorder would have to have a parent who also has the trait. So now let's take some of these ideas and let's apply them here. So here, okay, so I'm following along on my screen here. Okay, so here, one thing that you notice about this pedigree is that it's mostly males who have it. So the pattern of inheritance here, so first of all, 1, 2, 3, males have the genetic condition, and it also skips a generation. So given those two ideas, the fact that there's a disproportionate number of males and that it skips a generation makes this sex-linked recessive. And how were we able to determine this? So there were more males than females. And it also here skipped a generation. So if we have this son, then these parents, then these grandparents, it skipped over the parents. So for number 1C, if a couple in generation 2 were to have another child, so here's generation 1, 2, and 3. So if these two people were to have another child, what is the chance that they will have a male with the disorder? So now we have to assign the genotypes that we know. So males are much easier to assign genotypes to than females when it comes to sex-linked recessive pedigrees. So these two males both have a condition. So we can put X lowercase r, Y, X lowercase r, Y. You could also use A or B. The letter doesn't matter as much as whether you write that it's uppercase or lowercase. So these two males have the condition. This male does not have the condition or the trait, so he's X capital R, Y. This female does not have the condition, so we know she must have a dominant allele. Now we need to determine the other one. In order to have two sons that have the allele, it has to come not from the father, but from the mother. So here's the couple in generation 2. If they're to have another child, what's the chance they will have a male with a condition? So here is the Punnett square that we set up. Here's a female carrier and a normal male. So homozygous female, a carrier female, a normal male, and a male with the condition. So the chances there are 25%. If this couple has another child, what's the chance that they will have a carrier? So only females can be carriers, not men. So that would be this individual here, and that's 25%. Now, 1E, the couple in generation 2 know they are having a female. So that's a given, and that's a known. So now let's focus on the females. What's the chance that she will be a carrier? So now we focus on the females, and out of the two females, one is a carrier. So that's a 1 in 2 chance, or a 50% chance. Now, this is just connecting to what we were talking about before, but what types of genetic disorders follow this pattern of inheritance? So Duchenne muscular dystrophy, color blindness, and hemophilia, which we had noted is common in the royal family. Okay, so now going on to the next page. Okay, I'll keep this here. And we see another pedigree. We do not see that there are more males with the condition. We do not see that anyone with a condition also has a parent with a condition. We do see that it skips a generation. So we cannot say it's dominant, because if it were dominant, then this person would have to have a parent with a condition. This person would have to have a parent with a condition. So it's recessive. And in this case, more females have it. So it really would be autosomal. So here's an autosomal recessive pedigree. These parents cannot have an offspring if it were autosomal dominant. They could not have an affected offspring if they were autosomal dominant. So how were we able to determine this? We see that it does skip generations, and it's roughly equal males, females. What types of genetic disorders follow this pattern of inheritance? So PKU, genetic disorder where there's a buildup of phenylalanine in the brain. Cystic fibrosis. So there is a faulty ion channel in the cells and leading to a buildup of mucus. And sickle cell anemia, where the cells, the red blood cells, become stiff in shape and they don't flow through the capillaries as well. So now the couple in generation 3, okay? So here's generation 1, generation 2, generation 3, and generation 4. So the couple in generation 3 are those two. They're expecting another child. What is the chance that the child will have the genetic disorder? So we have to determine their genotype, and we'll do that. So the two children, this daughter and this son, both have the condition, so they must be homozygous recessive. If they had a dominant allele, they would not have the condition because it's recessive. Both of the parents do not have the condition, so they must have a dominant normal allele. But in order for them both to have a child with the condition, both parents must be able to pass down a recessive allele. So here is the Punnett square we can set up, and basically both parents are carriers. So heterozygote and heterozygote, and that's what we get. So what's the chance they will have a child with a genetic disorder? And that would be this child right here. So there's a 25% chance. Now, this couple they know that they are having a daughter. What's the chance that she will have the genetic disorder? It's still 25% because since it's autosomal, gender doesn't matter. What must be the genotypes of both parents in generation 1? So here in generation 1, this parent is unaffected, this parent is unaffected, but they have an affected child. So both of these parents have a dominant allele. Oh, I'll stick with A's because I was doing A's. Sorry. Okay. So they both have a dominant allele, and yet they still have a child with the condition, so they're both able to pass on the recessive.